Hello everyone and welcome in the ProLEED Studio tutorial. Here I will show you ProLEED Studio software which I specifically created for simple and intuitive modeling of low energy electron diffraction patterns. It was actually done by experimentalist for an experimentalist to make our life much easier. The ProLEED Studio allows you to load your experimental diffraction patterns and directly use it for modeling of the real space lattice. You can use it to simulate distinct diffraction spot intensities in substrate or superlattice domains, and you can also use commensurate mode for pinning superlattice points to the substrate. And as you will see, you can also easily visualize real and reciprocal space vector, unit cells, grids, and scale bars, so it can be also used for educational purposes. I also made the software for simple data export, so you can export ready-to-publish images in both vector and bitmap formats. In this tutorial, I will go through all the ProLEED Studio functionality and 3 experimental examples as fast as possible to make the tutorial shorter. As I said at the beginning, my primary goal is to make lead pattern modeling easier, and I understand that the modeling of lead pattern is rarely a trivial task. So if you have any ideas for additional functionality, just contact me directly and I will be happy to discuss how to implement it. So let's get started.
When you run the ProLEED Studio software, the welcome window pops up and you can select the substrate type you want to use, or load your previous model by choosing the open button, or dragging your file into the welcome window area. In this tutorial, I will use the square substrate because at the end of this tutorial I will demonstrate all the modeling on the square substrate. On the left side you see a real space lattice arrangement, and on the right side a diffraction model. You can zoom the view using the drop-down menu on the top toolbar for both real and reciprocal space. Then you go back to the original view using the buttons next to the drop-down menus or the buttons under the views. Right-click on the view also brings the original view. When you hover the mouse over the real space, you see its x and y coordinates in angstroms under the view. It also shows the object name over which the cursor is. The same applies to the diffraction in inverse angstroms. The top left sidebar menu allows different operation modes. The first one is select mode, in which you can select an object. Selected object with its basic properties appears on the top toolbar. The second mode is move. In this mode, you can move with every selected lattice point or diffraction spots. The third mode is for zooming. By clicking and dragging, you can zoom the area in both real and reciprocal space and use object moving for precise positioning. The fourth mode is panning. By clicking and dragging, you can move your view, and right-click again brings us back to the original view. The fifth mode is locked for now and used for moving the experimental diffraction image. It can be loaded by clicking on the Open Image button, and now the fifth mode can be used for moving the diffraction image. This mode also prevents spot movements. I will remove the image for now. When you select a specific object, for example a real space background, the bottom color tab becomes activated and you can change the color. If you select real space lattice points, more properties appear. Color now is for the outer color and color in tab is for the inner color. You can also select the outline thickness. Lattice point sizes are changed using the top toolbar properties. By default, the ratio is locked, and when you change its width, the height is automatically updated. It can be unlocked by the buttons next to it. Mouse wheel is generally used for changing the selected object sizes, and it's very helpful. The last step for the lattice point is the center tab, where you can change the shadowing effect. Diffraction spot sizes can be changed in the same way, for example by using the mouse wheel. However, it has an extra possibility of fixed spot size mode, which can be changed to mirrored, and only these are changed. By using none, only selected is changed. To simplify the diffraction model comparison with the experimental data, the diffraction view has 3 additional buttons that switch between bright, dark and color projections. In color mode, you can easily change the spot color and their transparency. The same applies to the unit cells or their outline. The middle sidebar is used for a quick and simple manipulation with substrate objects. It allows to show and hide substrate unit cells and arrows. Arrow labels can be hidden using arrow properties. The third toggle button visualizes the substrate grid. Its thickness can be changed using the top toolbar properties or by mouse wheel. The last toggle button shows the scale bar in both real and reciprocal lattice. It can be dragged around using the move mode. Their properties, like font size or scale bar thickness, can be changed using the mouse wheel or in the Properties tab. The main superlattice parameters can be set by the bottom sidebar. You can show the superlattice, arrows, unit cells and grid similarly to the substrate sidebar. When you select the superlattice point, you can choose which superlattice vector remains fixed during the movement. In this case, it is the S1 vector. By switching to S2 to fixed, S2 vector remains fixed. The same can be used in the diffraction. Using the sidebar, different diffraction domains can be easily visualized by clicking B, C and D, or by clicking double-check toggle button that shows all domains directly. The superlattice spot sizes can be changed at the same time, but different size changing modes are also available. You can change to the individual domain or frequently used or mirrored mode, in which selected and mirrored spots are changed simultaneously in all domains. There is also an individual mode for selected spots in all domains. None mode for changing only selected spot. Switching between bright, dark and color diffraction views changes the colors of all superlattice points. The last toggle button in the superlattice sidebar pins the selected superlattice point to the substrate during its dragging. If you move the point around, selected spot is pinned to the closest substrate point and the diffraction button is instantly recalculated. Bottom Properties tab control is used for detailed parameter settings. It has tabs for different layers like background, substrate, superlattice, arrows, unit cells, grids and scale bars. The first one is the background. If I zoom into 50%, we see the plotted size of the real space image. If you need the bigger area, you can simply change it in the lattice width and height properties. If I, for example, set to 100 angstroms, we can see all the plotted lattice points. Their number can be changed in the lattice or the drop-down menu. The order scheme is shown in the bottom tab. The higher the order is, the more points are plotted. The same also applies to the superlattice or diffraction. The second tab is for substrate settings. The lattice section shows A1 and A2 vectors, lengths and their angles with respect to the positive x-axis. If I change to move mode and drag the lattice point, these numbers are instantly updated. You can change the A1 vector length directly in the input box, in the diffraction section, or in the input box on the substrate vectors. There are three different substrate type possibilities: square, hexagonal and oblique. In the hexagonal type, the real space unit cell angle is fixed to 120 degrees. In oblique, you can change all the necessary lengths and angle parameters. For now, I will go back to the square substrate type. Third tab for superlattice has similar sections to the substrate type. If you drag the superlattice point, all vectors and angles are automatically updated. The same is true for diffraction spots. Lattice vector sizes and angles with respect to the positive x-axis and the angle between S1 and S2 vectors can be directly set. There is also an additional section for visualization of diffraction domains, or pinning the superlattice to the substrate, and the matrix notation for the superlattice with respect to the substrate. Next step is for arrow settings. Lattice and diffraction arrows, their labels, arrow thickness, and label sizes can be changed here. If you select arrow or label, you can use the mouse wheel for updating. The domain section here allows the visualization of other domain vectors. The Unit Cell tab is used for showing and hiding all possible unit cells in real and reciprocal space. The Grid tab is used for showing and hiding substrate and superlattice grids. and changing their thickness. Scale bar tab allows us to show and hide the scale bars individually in the real space and diffraction, and also change their properties like font size, scale bar thickness and length. New model can be loaded by clicking the blank icon here or using the File menu and clicking the New menu item. Open and Save menu items are used for saving and loading the ProLEED models. If you, for example, are done with your model with specific diffraction spot sizes, arrows, unit cells for different domains, and you want to save it for further processing, you can either click on the Save icon or go to the menu and press Save. The model will be saved with the ProLEED extension. Later you can load the model by clicking the Open icon, Open menu icon, or by simply dragging the file into the ProLEED Studio. ProLEED Studio was built for the convenient export of ready-to-publish images in vector or bitmap formats. Using the Export item in the File menu, you can choose if you want to export real or a reciprocal space, and then you select the format. For the vector format, you can click SVG and set up your export parameters like image height and width and object clipping. For bitmap images, you can use PNG, JPEG, TIFF or bitmap formats. In this case, you set the image export width and its resolution in dots per inch. For convenient testing, the undo and redo actions are implemented. If the substrate or superlattice vectors are changed, the previous parameters are recorded. Using the undo arrow, you can go back in the history or redo if you need. The theme menu allows you to change to the dark mode of ProLEED Studio if you prefer it, or change the theme color. These settings are also saved if you open the application again. You can click the default menu item to get back to the default theme. The experimental diffraction image can be loaded into the diffraction model by dragging the image into the ProLEED Studio, clicking the image icon or clicking the File menu and selecting Import Diffraction Image, or by selecting the Image tab and pressing the Open button. When you load your image, you can change its size using the mouse wheel and drag the image using the mouse move image mode. Image can be also hidden or brought to the front. Transparency and image angle can be also changed. The image can be also flipped horizontally and vertically, and easily removed. In the first example, I will show you how to load and update scale bar to the substrate diffraction pattern. I will use silver 100 with fixed lattice constant. I will not change it further. I can load my experimental image, remove unit cells, and change the diffraction spot sizes and update the image size to keep the model scale. Now I can show the diffraction scale bar and suppress the spot visibility. We are basically ready to export both real and reciprocal space images. Now I will demonstrate the possibility of modeling of two-domain commensurate diffraction pattern. So first of all, I will load the diffraction pattern to show you what do I want to model. I will bring the image to the front and change its visibility. Again, we have 100 substrate, so these are substrate spots and the rest of it belongs to the superlattice domains I want to model. For now, I remove the image and load the micro diffraction image of individual domain. Now I change the image size to align substrate spots with modeled substrate. I also remove unit cells and arrows. I show the superlattice and change the color of superlattice pattern to black to distinguish between experimental and modeled spots, change their size, show superlattice vectors, and adjust label sizes. I switch to the move mode and zoom the model using Ctrl plus mouse wheel and make the first estimation of diffraction pattern model. When I take a look to the real space lattice, I see that the superlattice points are close to be commensurate. So I switch to the commensurate mode and using the mouse dragging, I pin superlattice points to the closest superlattice points, switch to the select mode and adjust spot sizes to simulate the distinct spot intensities. Switching fixed spot sizes mirrors mode ensures that all domains that are not projected right now will have the same spot sizes. Now I can also project the second domain rotated by 90 degrees and remove the micro diffraction image. When I switch to the bright diffraction mode, I'm getting pretty nice diffraction model that I can now compare with the diffraction pattern I showed at the beginning. As you can see, we have basically perfect match between the model and experiment. Slight imperfections here are caused by diffraction image distortions, so it's always good to compare mutual positions of diffraction pattern at specific places. The reason of modeling of diffraction pattern is of course to get real space lattice arrangement, so we can now visualize the lattice unit cell. In the last example, I don't want to scare you with the complexity of diffraction patterns, but encourage you to not to be afraid to model more complicated ones. So here I will try to find the real space periodicity of this diffraction pattern measured again on silver 100 substrate. For now, I will load the micro diffraction image of single domain and update its size to align substrate spots as usual. I will show the initial superlattice model I created by simply dragging the spots and updating their size. In real space and also in the matrix notation, you can see that we are basically modeling Moiré pattern unit cell, so I will also show its unit cell. Now I will try to position diffraction image, but you can see that we still have some image distortions. Now I remove the image and project also other domains in the diffraction model. Also switch to the bright diffraction mode. Now I load the diffraction image and compare it with the model. For now, considering the image distortions, we have pretty good match with the experiment. However, the mutual positions of diffraction spots are generally not affected by projection system, so we can use it for precise modeling. I will zoom the real space and use the commensurate mode for moving. When I change the real space unit cell slightly, you can also see slight changes in the diffraction pattern that we can now use for precise real space modeling. If I zoom in, for example, this diffraction pattern area and show the diffraction image spots and move them a little bit, we can see that these mutual position spots do not correspond to the experimental data. So I will try to move the lattice point around to get the match. And I see that they match for this superlattice unit cell. As this pattern is pretty complicated, you can also focus on different places and do the same thing there. For example, positions of these 4 spots correspond, but when I move the lattice point around, their positions are really sensitive to that. So I go back to the previous superlattice arrangement. So this is how we can precisely analyze such complicated diffraction patterns. I can remove the image and also show the scale bar. And the model is ready to be exported. The last thing I want to mention is the possibility of enlarging the real or reciprocal space view for more precise modeling.